Hey students, welcome to lecture number 9 of multiple zeta values and modular forms. So today we want to finish with section 3, where we talk about linear relations of or families of linear relations among multiple zeta values. So last time we talked about extended double shuffle relations, where we used these regularized multiple zeta values. So recall that we had this zeta map in section 2 from the space of admissible words to the real number, and last time, or the time before, we extended this map to the space H1 and had two maps, the shuffle regularized multiple zeta value and the stuffle regularized multiple zeta value, and they gave us polynomials. And then we saw last time that there are these extended double shuffle relations which generalized these finite double shuffle relations we did in section 2. And today we want to talk about more families of linear relations. And for this I made some overview of different families of linear and also algebraic relations. So let's see in this picture here what we already know. So last time we talked about these extended double shuffle relations. So we had bullet was either shuffle or stuffle, and then for a word in H1 and a word in H0, this W shuffle U minus W stuffle U. So this was a word in H1, and then we could apply one of these regularized multiple zeta values, and this was a polynomial in T. And the statement was that this is a zero polynomial, and the coefficients of these polynomials were given by multiple zeta values, and therefore this gave linear relations among multiple zeta values. And these generalized these finite double shuffle relations, which we saw in section 2. So this just worked when both of these words were in H0, and then we thought that this zeta map is an algebra homomorphism with respect to both products, the shuffle and the stuffle, and therefore we obtained these finite double shuffle relations. But we also saw that they were not enough to give all relations among multiple zeta values, but we expect that these extended double shuffle relations give all relations. So let me maybe circle the ones we already saw. So the orange ones we saw. And also we had this algebraic relation here, this Euler relation in the very first lecture. And also last time, as a special case of the extended double shuffle relations, we saw this Hoffman relation here. And also we had this duality relation, which we will also talk about today. And here in this overview, so let me zoom out, there's some explanation here. So you see the ones with a red border, some families here have a red border. There we expect that they give all relations among multiple zeta values, so for example these extended double shuffle relations. But there are also other families of relations where we expect that they give all relations. But due to lack of time, I will not talk about all of them in this lecture. But what I want to talk about today is again this duality. And for example, one open problem we mentioned last time. So even though we expect that all relations follow from this extended double shuffle relations, we don't know how to get from extended double shuffle to duality. Okay, so today what we want to talk about is the right-hand corner here, about the so-called Ohno relations. And also here on the bottom we see the sum formula. And we also want to talk again, as I said, about this duality. And we will start with this duality. And so remember, the proof of this duality relation was based on the fact that there was this, if I have a multiple zeta value, I could write it as some iterated integral. And then by a change of variable in this iterated integral, we obtained this duality relation. So and today, so let's say today, we want again talk about this duality, but today we want to use the original definition of these multiple zeta values as in sum, And the concept we will be using or introducing today is a so-called connected sums, which was recently introduced by Seki and Yamamoto. And with this nice concept, we will also prove these Ohno relations. And these we will not just prove for multiple zeta waves, but also for their Q analogs. And we will see that these Ohno relations, they generalize the duality, but these Ohno relations also generalize the so-called sum formula here. So we will also see this part here. And also today in the archive, on the day of the recording of this lecture, you can see two papers which are related to this picture here. So you can see here in the archive that there's a paper by Hirose, Sato and Seki on this part here, on these double Ohno relations. And in this paper they also use this concept of connected sums. And also you see this paper by Seki-san titled Connectors. So today we will just talk about one or two certain types of connected sums, but there are several different types of connected sums. And in his overview article you can find a nice overview about where these connected sums also can be useful in other types of relations. Okay, so let's start. So this overview you can find in the lecture notes, and also you see these numbers here. So for each of these numbers I either give some short explanation, or I give you the reference where you can find more on this type of or this family of linear relations. Okay, so let's start by talking again about duality, but now from a different point of view. So what was the duality relation? So recall, to state the duality relation, we introduced this anti-automorphism on the space H, but then we also saw that this is defined on the space H0. And this anti-automorphism interchanged these x and y. So for example, tau of the word z3. So z3 was the word xxy. So anti-automorphism means we need to inverse the word, and we need to change here the x and the y's. So xxy becomes xyy, which, if you write it again in the Z alphabet, is z2, z1. And then the statement of the duality relation was that the zeta map applied to some word equals zeta of tau of this word. So and therefore this one here gives the relation that zeta 3 equals zeta 2, 1. And now we want to phrase this duality relation on the level of indices. So here it's on the level of words. And for this, so let's assume we have an admissible index, k admissible. And now we want to understand what is somehow the dual index of this admissible index. And for this, so if I have an admissible index k, then the first claim is that I can write this index as follows. So because k is admissible, it will start with a number which is greater or equal to 2. Therefore there's some a1 here, greater or equal to 1, such that we start with a1 plus 1. And then maybe there will be some 1s after this. So this means I have b1 minus 1 1s there. But it could also be the case that there are no 1s, and in this case this b1 would be 1. And then I have again a number greater or equal to 2, maybe some 1s, and so on. And then maybe at the end I have some 1s. And now with this description of this admissible index, so any admissible index can be written like this with some a's and some b's, we now define the dual index, denoted by this k dagger. And what we do is, so this is also an admissible index, and it starts with bs plus 1. So bs was here the number of 1s minus 1 at the end of this index k. Then I take here the as, number of 1s, and so on, and I end here with a1 minus 1 ones. And the claim is that that tau of the word attached to this index is exactly the word attached to this k dagger. And why is this the case? Well, because here, so this is an exercise, but the rough idea is if I start with a plus 1, so this means if I write this as a word, I have some x's, x, 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 y, and here I have exactly a1 x's. Then I have maybe some y's. So this is b1 minus 1, and in the end I have x, 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 y. So here I have as x's, because this is then as plus 1, and then maybe I have some y's, which gives me the numbers of ones here, which is then, so this is bs minus 1. So if I apply tau to this, I need to reverse the word, and I need to interchange x and y's. So therefore tau of this, thing, it will start with x, 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 bs minus 1, but this also gets to an x, so I have exactly bs x's, bs, and then the first x here of this as, this becomes a y, so therefore the first index here I get is bs plus 1. And then here I have some y's, which is exactly as minus 1. And so on, and that's why that's how you see that you get this index here. So in other words, duality with these indexes can be stated as follows. If k is admissible, then zeta of k equals zeta of k dagger. Okay, so this is now just a reformulation of the duality. So and now what we want to do is we want to give another proof of the duality by using so-called connected sums. And we will just start by giving the definition. So if I have two indices, k, which is now an arbitrary index, k1 to kr, and l is also an index, l1 to ls, and they are both non-empty indices, but they don't need to be admissible, then we define the connected sum denoted by zkl. And this sum looks like this, so it's a doubled ordered sum here. So if you forget this part here for a second, then this is nothing but the product of zeta k and zeta l, because here this part is just zeta k and this part here is just zeta s. So we have these two sums, but they get connected by this factor here. So without this factor, these m and these n would be independent, but they get connected here at these largest summand by this part here, and this part is called the connector. So this here is called the connector. And we will also use the notation CMN. So this connector in this case is called S, is given by m factorial n factorial divided by m plus n factorial. So it's basically just a binomial coefficient inverted. And then we also define, so this we define for non-empty indices, but we also define if k is admissible and this entry L is empty, we say that this is the same as z empty index k, and this we define to be zeta k. Okay, so also notice that this is symmetric, so this is the same as z L k. Okay, and why do we do this? So the idea is that we will start with some zeta value, zeta k, which here by definition is z, the connected sum where we put the index on the left, and then we have some empty index here. And then we will show that these satisfy so-called transport relations. So what we want to do, we transport the index from the left-hand side to the right-hand side. So there will be some steps in between. And then we will end, so on the left-hand side we will have an empty index. And after transporting the index from the left-hand side to the right-hand side, we will not get the same index, but we will get exactly the dual index, k dagger. And this, by definition, is zeta k dagger. And then we see that zeta k equals zeta k dagger, and therefore we get the duality. And here, what I want to explain now is what these transport relations are. So how do we transport this index from the left-hand side to the right-hand side, and why do we get the dual index there? Okay, and here they are. So if I have two indices, k and l, then if the second index is non-empty, then the first transport relation is that the connected sum, if I start with a 1 here, and I have the index k here and the index l here, then I can transport this 1 to the beginning of the index l by adding this 1 to the first index of l. So this is the first transport relation. And the second transport relation is, if I have a number on the left index here, so here we assume that the left index is non-empty, and if it starts with a number greater or equal to 2, then I can subtract this 1, and I could put this 1 in front of the right index. So first notice that these are actually not two different relations, it's just written the other way around. So because this z is symmetric, this relation here is exactly the same as here. So in the proof we just need to prove one of them. But now let's see what happens if we actually start with some zeta value, and what does this have to do with the duality. So let's start with our standard example, so zeta 3. So zeta 3 is the connected sum 3 empty. And now, so now I have an index on the left-hand side which starts with something greater or equal to 2. So I can write it as 2 plus 1, and the 1 I can put in front of the right index. So I can split up the 1 and put it there. And then I can use it again because it's still greater or equal to 1, greater or equal to 2. So I can split up another 1, and I can put it again in front of the index on the right. But now I have an index on the left-hand side starting with a 1. So instead of putting this 1 in front, I will add the 1 to the first index on the right. So in this case, I get z. So here I get now the empty index because I have removed the 1 from there. And on the right-hand side, I get 2, 1. So I have empty something, and therefore this is zeta of 2, 1. And you see this gives the relation, the duality relation, that zeta 3 equals zeta 2, 1, after transporting the index 3 to the right-hand side, and it became the dual index of 3, 2, 1. Okay, so now let's prove this. And so and this is now really the beautiful thing about this. The proof is really really simple, because it really basically just uses this one equation here. So let's consider this sum here. So notice this here is basically just the connector CAN. So if I have numbers n greater or equal to 1 and m greater or equal to 0, and I take the sum, a goes from m plus 1 to infinity, of this part here, 1 over a times this factorial, times this connector here, then I can rewrite this, so you can check that that this is just the same by bringing this here on the same numerator. You can check that this part together with this 1 over n is exactly this. But here you see that this is a telescope sum, because here I have the same term, like, so this is the same term as this term here, except the a is 1 less here. So if I take the sum, a goes from n plus 1 to infinity, so everything cancels out, except for the first term where a equals n plus 1. So in this case I still have this one here. So if I set a to be n plus 1, then I get exactly this thing here, and this, notice that this is the connector Cmn. Okay, so we have this equality here, and now we want to use this to prove the first transport relation. So we want to prove that this equals this. So let's just calculate what this is. So by definition, this one here, I will call it A, m1 up to mr greater 0, and here I have n1 up to ns greater 0. And here at the beginning I have the connector of these a and n1, and I have 1 over a, because 1 over a corresponds to this 1 here, so it's 1 over a to the power 1, so this is the 1 here, and the connector Can, and then 1 over m1 k1 mr kr, 1 over n1 l1 ns ls. Okay, but now we can see here that we can take the sum over a, so a goes now from m1 plus 1 to infinity, and here we have exactly this term here. So this sum here is exactly given by this sum here, so therefore we can replace it by this here. So so using this equation there, we get, so we don't have a sum over a anymore, it's just a sum m1 mr greater 0 and n1 ns greater 0. And now we have the connector of m1 and n1, and here we have m1 k1 mr kr. And now because we have this 1 over n, so n in our case here is, oh, here I should write this is n1, sorry. So we have an additional 1 over n1, and therefore we get here n1 to the l1 plus 1, n2 l2 up to ns ls. But this is exactly what we wanted. This is exactly now the connected sum, which on the left hand side has the index k, and on the right hand side it has the index l, but in the first entry we got plus 1. So this is the first transport relation, and the other one follows by a symmetry. And now we want to understand why this proves the duality in general, because so far we just had this one example with zeta 3, and this accidentally we got the dual index here. But let's see why this works in general. So if I have, so we discussed how this, so if I have an admissible index, I can write this like this with these a and b's, which are greater or equal to 1. So therefore zeta of this index k can be written as a connected sum like this, where I write the index on the left hand side. And now I start with something which is greater or equal to 2, and therefore I use the second transport relation. And actually I can use it exactly a1 times. And then after this, after using the second transport relation a1 times, I will have a 1 at front, and actually I will have exactly b1 once in front, so I can use the first transport relation b1 times. And this will, so if I use a1 times the second transport relation, I will have exactly these ones here, a1 minus 1. So if I use it a1 times, then I have a1 once there, but then I will use the first transport relation, which adds a 1 on front of them, and this will give the 2 here. And yes, so this is the first step where I use it A1 times, and then I use the second relation B1 times, and I get this one here. And then again you use the second transfer relation A2 times, and the first one B2 times, then A3 times, B3 times, and then in the end you will see you get exactly the dual index, which then gives a zeta k dagger. And therefore we get the duality just by using these transport relations. Okay. So now we want to use this idea of connected sums to prove a more general statement which generalizes the duality, and this is known as the Ohno relations, or Ohno's relation. And this relation also generalizes the so-called sum formula, so which was, as far as I know, first conjectured by Michael Hofmann, and then it was proven by Granville and Zagi independently. And the statement is that if I fix a weight k and depth r, then the sum of all admissible multiple zeta values in a fixed weight k and a fixed depth r is always given by the single zeta value zeta k. And again, the one relation we always use, zeta to 1 equals zeta 3, is one example of this, because in a fixed depth 2, this is the only admissible index, and therefore for this the sum formula should be zeta of this weight, in this case 3. And this we now want to generalize to this so-called Ohno relations, and for this we need some notation. So we will introduce the following. So if we have some admissible index k, then we define the so-called Ohno sum, which we denote by Oxk, which is given by this formal power series with coefficients given by this OKC. And this OKC for c greater or equal to 0 is just the sum where I add c's to this index k such that these c's sum up to c. So this k is a fixed index, so it has a fixed depth r, and O of this index k for a fixed number c is just all possible ways to add the weight c into on top of this index. And therefore this is a multiple zeta value of weight given by the weight of this index k plus this number c. So in general, this Ohno sum is a power series with coefficients given by multiple zeta value, and the constant term, so what is the constant term? O0 of k, this is just a zeta k. So, I mean, for example, what is OX21? This is zeta to 1, the constant term, plus, and now the coefficients of x, so in the case c equals 1, I can add the weight 1 at different places, so I could put it on front, 3, 1, or I could put it at the end, so zeta 2, 2. And then what is the coefficient of x squared? So I could add the weight 2. So either I could add 2 1s, or I could add a 2 at the first or the second place. So for example, if I add 2 1s at each position, it would be 3, 2. If I add a 2 at the beginning, it would be 4, 1. And if I add a 2 at the end, it would be 2, 3. And this would be the coefficient of x squared, and so on. Okay, so now let's consider a special case. So if k is the index given by 2, and then r minus 1 once, so it's 2, 1, 1, 1, 1, 1, and now consider C to be k minus r minus 1. So in this case, what is this coefficient? So this coefficient here, O of this index C. So the question is, if I take this index here, 2, 1, 1, 1, 1, and now I can add the weight k minus r minus 1. So the total weight, so this has weight 2 plus r minus 1. So it's r plus 1. And if I add k minus r minus 1, then the total weight of this guy here is weight k. And what this is actually, it's the sum of all admissible indices in weight k, because here this is somehow the smallest admissible index, and I add all possible weight such that I end up in weight k. So what this is actually here the left hand side in the sum formula. So I can copy it here and put it here. So this is exactly, so this coefficient is the left hand side of the sum formula. And now, what is k dagger in this case? So we learned when we first talked about the duality that the dual of this 2, 1, 1, 1 is exactly just the index of depth 1. So this is just k r plus 1. So this is just an index with one entry, r plus 1. And what is in this case, so O k dagger of C? Well, if I add this to this, then I also have weight k, but there's not much possibility. I just have depth 1, so this is just a zeta k. Okay, and here we see by the sum formula that this is actually the same. So if we would consider the Ohno sum of this example, so Ohno sum of this thing here, we would start with zeta k, and then at some point we would have this index here, and this would be the coefficient of x to the k minus r minus 1 plus something, and the Ohno sum of k dagger in this case, the constant term would be zeta k dagger plus, and then the coefficient of x to the k minus r minus 1 in this case is zeta k, x to the k minus r minus 1 plus, and other coefficients. So in this special case of this index, we see that the Ohno sum of this index k and the Ohno sum of this k dagger, they at least have the same constant term, because by duality we know that zeta k equals zeta k dagger, and they also have the same coefficient here by the sum formula. And the Ohno relation now states actually that this is the same, meaning that also all the other coefficients are the same. So the statement of the Ohno relation is that the Ohno sums also satisfy the duality. And then by the example before, we see that this generalizes the duality by looking at the constant term, and it also generalizes the sum formula by taking this special index 2, 1, 1, 1, and looking at this coefficient of x to the k minus r minus 1. And so let's do another example here. So this example number pi. So for example, if I have this index 2 to 1, then the dual index is 3, 2, because 2 to 1 is x, y, x, y, y, and then changing this is x, x, y, x, y. And the Ohno sum of 2 to 1 is given, well, it starts with zeta 2 to 1, then I can add 1 at each position, and here I can add 1 at each position, or I can add 2 and 1. I can add 1, 1 at each at the positions, or I can add 2. So this is the coefficient of x squared, and the Ohno sum of the dual is given by this, so the constant term is duality. But here we also get the relation that this for example, equals this. So this gives a relation in weight 5, which is not the duality and which is also in this case not the sum formula. So we get a lot more relations among multiple zeta values, and these relations you can count. So we can make this table, which was created by Tanaka, and so we can count the Ohno relations. So here in the fixed weight k, we get in weight 3 we have this one Ohno relation, zeta 3 equals zeta to 1, and in weight 4 we can get two relations, but we also see, in comparing this to all conjectured relations, that this is actually not giving everything. So in weight 4 there's one more relation which we do not get from the Ohno relation, and this one relation is given by this finite double shuffle relation, which comes from the product zeta 2 times zeta 2. Okay, so now, so this was the Ohno relation and we didn't give a proof yet, and instead of giving the proof or sketching the proof of this one here, we will sketch the proof of the Ohno relation for Q analogs, which generalizes this by sending Q to 1. So recall first, what do we mean by Q analog? So we discussed different types of Q analogs, and most of the time we talked about these Q series G, but we also introduced this Q multiple zeta waves, this Bradley-Chow model, which was defined for an admissible index k. We denoted it by this, and then it was given by this sum here. So recall that this m here is a q bracket, or the q integer, which is given by 1 minus q to the m divided by 1 minus q. So this is if q is an integer, just given by this, and if we send q to 1, this just gives m. So here we saw that if we send q to 1 of zeta q Bradley-Chow of an index, this just gives the multiple zeta value. And the reason why we talk about this model now is because this is somehow the unique, in a certain sense, Q analog model for multiple zeta values, which also satisfies the duality and which also satisfies the Ohno relation. So therefore, to state the Ohno relation for this object, we also need to somehow define the Q Ohno sum and then give the proof of the Ohno relation. So for an admissible index k, we now define the Q Ohno sum, which we denote by OX, but now we also write a Q here. And we again write it as a power series like this, but now the coefficients are not multiple zeta values, but they are given by formal Q series. And this OQ is given by, it's exactly like before, but instead of taking the sum over multiple zeta values, we take the sum over this Bradley-Chow model. So this is a formal power series in X, where the coefficient is given by formal power series, but you can also check that this sum absolutely, that this gives a real number and converges in the case when this Q and X are real numbers between 0 and 1. And also we see that if we send Q to 1, this is exactly the Ohno sum we saw before. And now the statement is that this Ohno sum, the Q Ohno sum, also satisfies the duality, meaning we have the Ohno relation for Q analogs. So here, for any admissible index k, we have that the Q Ohno sum of some index k, of some admissible index k, is given by the Q Ohno sum of the dual index. And now we want to sketch the proof of this, and the strategy using connected sums is always as follows. So the main goal, or the main task, is to find a suitable connected sum, which basically means to find a good connector. So we want to find a connected sum, which will be something depending on two indices like before, k and l. where if one of them is the empty index, we will just get back our original object. And then we want to show that these connected sums also satisfy the exactly same transport relation, and then we will be able to transport one index from the left hand side to the right hand side, and it will become the dual index, and then we will show this Ohno relation. Okay, so let's find this connected sum. So this family relation here was first proven by Bradley using some polylogarithm, Q polylogarithm, and but the proof we will show now is due to Seki and Yamamoto, and I think it's a much nicer proof than the original proof. Okay, so let's see. So we want to define the connected sum. So first we want to rewrite the Q Ohno sum a little bit. So here this was the definition. So we had this Q Ohno sum given by this power series where we had as coefficients these OQs. And these OQs were the sum for fixed C over all possible ways of adding C's to this index K. And therefore, instead of taking the sum over C, we can take the sum over all C1 to CR and replace the C by C1 plus C2 and so on. So this is the same. And now let's open this. And then we can plug in the definition of the Q analog, which is just given by this here, and we have this ordered sum here. So this is just plugging in the definition. And then we can take the geometric series over the C's here, and we see that this sum here is just given by this ordered sum with these factors here, which just come from taking the geometric series with respect to the C's at each place here together with this x here. So, and this we also want to, we want to give it a name. So these factors, where's my S? It's here. So this we just denote by an ordered sum over these summons, which depend on the index K and the M. And this is just given by these factors here. So notice that if x is 0 and q is 1, then this skm is just 1 over m to the k. Because here if x is 0, this term vanishes, and then I have mq to the power k, and there if I send q to 1, this is just m to the k, and sending q to 1 here is just 1, and therefore this is just 1 over m to the k. So in particular we see, or what we also saw before, which you can see here, is that the Q Ohno sum of 0, 1 is just the multiple zeta value zeta k. So these things are somehow the analog of 1 over m to the k, and therefore we now want to find the right connected sum. So the main idea is, of course, we replace this single sum here by a double sum, where you also have n1 greater than n2 up to ns, and also takes these s, but we need a connector. So we want to find a connector C, which depends on, so we want to find something like this, such that this gives back our connector as before. So this we denoted Cmn. So this was m factorial n factorial divided by n plus n factorial. Because the case x equals 0 and q equal 1 is the classical case, and we want to somehow find this with this property here. And this was done by Seki and Yamamoto, and they defined the following connector. So this Cxqmn is given by this expression here, so we have some q to the mn, and then we have this fxq, where this fxq is given by this product here. So this somehow corresponds to the factorial, because here this in the special case 0 and 1, this is just m factorial. And then you see that this connector satisfies exactly this property here. Okay, so now we have all ingredients to cook our connected sum. We have somehow the summons here, and we have the connector. So it's somehow now straightforward to define what we mean by our connected sum we want to use. So let K and L be, again, two non-empty indices. Then we define, where I now call it here, the connected Q-Ohno sum, which is now the Ohno sum, Q-Ohno sum, depending on two indices, by taking, as I said, these two sums over ordered m's and ordered m's, and here we have this s, so somehow these summons. And now we take this connector we mentioned before, which was given by this expression here, where we had somehow this qx analog of this factorial. And also, if one of these indices is the empty index, we just define this to be our Q-Ohno sum. So this is the Ohno sum, and now the statement is they satisfy the transport relations, which are exactly the same transport relations. So if we have an index, the second one is not empty, I can transport the one from the left to the right, and if I have something starting with some index greater or equal to 2, I can split off the 1 and put it here in front. And the proof of this, so this is now homework, but the proof, if we go back here, so this was the original proof, and so you will see, if you do the homework, that this sum here, if you replace this connector by this xq, and this, instead of 1 over a, you need to replace by this summand, you will see that the same argument holds, that you get a telescoping sum here, and then you get the summand of this n here, and this connector xq. And then you can use the exact same argument. And therefore, the Ohno relation holds for this Q-Ohno sum, and therefore also the duality for this Q analogs or the sum formula hold, and also this gives another proof of the sum for the Ohno relation for multiple zeta values by sending Q to 1, and therefore also another proof for the duality. So this somehow generalizes everything we saw before. Okay, so this was the main part today. So if we go again to this zoo of relations here, so what we saw now is we talked about this Ohno relations here, which generalize this duality, and we also gave a new proof of the duality without using the iterated integral representation, and we also saw this sum formula here. And in this picture here, these arrows mean that we know that this relation implies the other one, so we see that there are much more relations in between, so there's some restricted sum formula which generalizes the sum formula, and this also follows from the so-called derivation relation, which is a consequence of a quasi-derivation relation, which is a consequence of this linear part of Kawashima's relation, which is a consequence of the Kawashima's relation, where we expect gives all relations among multiple zeta values. And in the lecture notes, you can find more on these relations. So in particular, I explain what these rooted tree maps by Tanaka are. So they generalize also these derivation relations, and they also have to do with some Hopf algebra structures appearing in theoretical physics, and they assign to some rooted tree an endomorphism on our space H1. And so in the end here I want to give an example of these derivation relations. So as I said in the lecture notes, for each of these points I give some explanation. So for example, for this derivation relation, point number 17, so this was first proven by Ihara Kanekonzagi, and the statement is that we can define derivation on the space H, and so with respect to the concatenation product, and therefore we just need to define the derivation on the generators x and y, and the rest is then defined by using this Leibniz rule. And in this case, for an integer n, the partial nx is given by this word here, and the partial ny is given by the negative. And then the statement is, if I apply this derivation to some admissible word, then this is an element in the kernel of the zeta map. And here I just give one small example. So if n equals 2, then partial 2 of x is xxy and xyy, and partial 2 of y is negative of this. So then we can try to apply it to the admissible word xy. And then we need to use the Leibniz rule, so we need to take a partial 2 of x and then multiply it with y plus x partial 2 of y. And then we can already use the definition on the generators here. So this is x y y plus x y y y, and then minus, and then we put x here in front of these guys, so x y minus x y y. And we see this part here cancels out, and we just get these two words, which if we write it in Z alphabet is Z2 1 1, and this is Z4, so minus Z4. And the statement of this derivation relation is that this is in the kernel of the zeta map, but this is what we know because zeta 2 1 1, which is also duality, is zeta 4. Okay, and so that's all for today. And yeah, so next time we will start by going to the next chapter, number 4, where we will concentrate on relations among double zeta values. And so we will ask ourselves, if we just have these extended double shuffle relations in devs 2, what kind of relations can we obtain? And are there other objects out there which also satisfy these type of relations? And this will lead us to the so-called double Eisenstein series. And also we will see that there's a connection to so-called period polynomials of modular forms. And then we will see this part in the picture here, that there are so-called exotic relations which come from cusp forms. And this we will maybe not do next time, but we will start preparing to explain these types of relations. See you then.